Hey, Calculus, Mr. Florio. We're gonna start chapter 6, and we're gonna kind of go to just do a few things in the chapter. We're not gonna go too in depth in differential equations, but hopefully you saw the video before the con video, kind of introducing what a differential equation is and what a solution is. In this video, I'm just gonna hope to find out a strategy to come up with a solution to a differential equation. And in differential equations, if you ever took a class that's just about differential equations, you just learn a bunch of different techniques that work sometimes, but there's no technique that really works every time. The one we're going to work on in this video is separation of variables, and we're not going to do slope fields. So, anyways, in the video with the Khan Academy video, it's all right. This is what a differential equation looks like, and here are some solutions to it, and let's check if they work. The goal for today is, can we find our own solution? So we've done this before. It's going to get a little trickier as we go on, but the first example is very similar to one we've done before. If the derivative of the function is this, what's the particular solution to the function given that it goes to the point 1,4? So what we're going to do is first rewrite the derivative of y as dy dx. This isn't something that you have to do, but I think it's a good way to look at it. And then if I multiply both sides by dx, what I'm doing is getting the y variable on the left side and the x variables on the right side. And now the goal is to integrate both sides. So this is a legal operation. If I take the integral of both sides, what do we get? And the antiderivative of, you can think of this as 1 dy if you want. The antiderivative of 1 would be 1y, or y, plus, I'm going to call this c1. I'll explain why in a second. And on the other side, if I take the antiderivative of this with respect to x is going to be 3x to the third over 3 minus 4x to the second over 2 plus some other c value, c2. Now, the reason why I'm putting these two c values, and we're not going to end up using two c values, is I can subtract the c1 on both sides to get the constant out of that side of the equation. And what I'm going to get is, let's see, that's just x cubed. That's going to be minus 2x squared. And if I take c2 and subtract c1, if I take a constant and minus a constant, it's just another constant. So I'm just going to call this third constant, I'm just going to call it c. You call it c3, call whatever you want. In fact, if you just call everything c, and it doesn't matter. We just have a constant at the end. Whether you get the constant by subtracting two constants, it's still some constant. And then the question is, all right, can we find out what the value of the constant is if I know that it goes to the point 1,4? So if it goes through the point 1,4, then when y is 4 and x is 1, we have y equals x cubed minus 2 times x plus c. And that's going to be 4 equals 1 minus 2 plus c. So 4 equals negative 1 plus c. Add 1 to both sides. That's c equals 5. So the actual solution is this equation right here. The particular solution is y equals x cubed minus 2x squared plus some constant. That some constant's going to be 5. So we've done this kind of question before where I've asked you to find the constant and put it back in. And that's finding a particular solution. That's finding one exact solution to this. Maybe there's other ones, but this is the one solution that also goes to the point 1,4. And making sure that it goes to 1,4, this is what the solution has to be. So that's the particular solution. In the next example, we're looking for the general solution, a solution that works in all cases. So we're not going to actually find a c value. So think to yourself, wow, we're going to have a plus c somewhere, or some constant somewhere. Going here, though, this might be something worth writing down before we do it. When we're doing a separation of variables, the goal is to first just write y prime as dy dx. and then we're going to group the x terms with the dx and the y terms with the dy. So you're going to separate your variable. That's why they call it separation of variables. And then when we integrate both sides, don't forget the plus c. And then if possible, we're going to isolate y. And I'll show you an example where it is possible and an example where it's not possible. So step 1, rewrite y prime as dy dx. And then I want to get my y's together, my x's together. So if I multiply both sides by y, my y's would be on the left side. If I multiply both sides by dx, I'll get rid of the dx on this side, get rid of the y's on that side. And now everything's, the y's on the left side, I have y dy. On the right side, I have x squared dx. And then we just need to integrate both sides. That was step 2. And the antiderivative of y is going to be 1/2 y to the second plus c, but I'm just going to do the plus c on the right side. The antiderivative of x squared is 1/3 x cubed, or x cubed over 3. And we have some constant here. And I'm going to call it constant 1 for a second because I'm going to do something to it. Just to clean this up, all right, it says solve for y if possible, and I think it's going to be possible here. Where are you? So isolate y if possible. We've done step 1. We wrote as dy dx. We grouped the x's and y's on each side. We integrated, and now we need to isolate y. So if I want to multiply both sides by 2, that's fine. I'm going to have y squared equals 2/3 x cubed plus 2c2. If I multiply a constant by 2, it's still some constant. So I'm just going to call it, c2 for it's still some constant. And then if I want to get rid of y, or if I want to get rid of the squaring, I'll just square root both sides. If I square root both sides, I got to include the plus or minus. I guess instead of calling that c2, I'm just going to call it c. So y is plus or minus the square root of 2/3 x cubed plus c. Am I sure? Well, I didn't actually do this on my own, but I think I can do it on the fly. Let's check it. The book says it's a really good idea to check your solutions in this section. So I need to plug these values into this equation right here and see if it works. So knowing that y is this, we'll work in this equation. And let's just look at the positive square root for now. This is really 2/3 x cubed plus some constant to the 1/2. And if I wanted to take the derivative of that, that's going to be 1/2 all this junk to the negative 1/2 times the derivative of the inside, which is going to be 3 times, that'll give me just 2x squared. Because the 3 times the 2/3, the 3's will cancel out and I'll get the 2x, and then just subtract 1 to the power to get x to the second. So let's check. Y prime, which we just said is this right here. By the way, the 2's are going to cancel out. So y prime, does y prime equal x squared over y? Well, y prime is x squared over 2/3 x to the third plus c, and it's the square root of that, right? If I bring the negative 1/2, bring it to the denominator, it becomes positive 1/2, and the positive 1/2 will still be a square root. And is that the same thing as x squared over y? And y we said is this right here. Y is the 2/3 x cubed plus c, and when you take it to the 1/2, it's the same thing as square rooting. And yeah, these things actually are the same. It is not a question. It is true. So we did solve the differential equation. The left-hand side and the right-hand side really are the same, as long as y is this value right here. And it doesn't matter what c is. There's a collection of functions that could work here. Any c value will work. All right, so this last step here said if possible. This next example, I believe it's going to be impossible, or is it the one after? That's the one where it's impossible. All right, so this one will still be possible, I think. All right, so get rid of some algebra. Step 1, rewrite y prime as dy dx. Step 2, separate the variables. So I'm going to multiply both sides by dx. We'll do this one step at a time for now. Now, to get the y on the other side, I can divide both sides by y. To get rid of the x squared plus 4, to put that on the side with the x's, I can divide both sides by x squared plus 4. And those will go away. And now I have 1 over y times dy. And you could either write this as 1 over y dy or dy over y. They're the same. And I'm going to write it like this because taking the antiderivative, I think, will just look a little bit better to me. Over x times x squared plus 4 dx. Okay, so we separated our variables, and now it looks kind of nice. I just want to integrate both sides. And the integration might be easy, might be hard. In this case, well, I guess you could be the judge. 1 over y, the antiderivative of that is the natural log of the absolute value of y, plus some constant. We don't need to worry about that. And the antiderivative of the right side, there's no way really simplifying this. We don't have like a quotient rule, but I do see this x squared plus 4. The derivative of that is 2x, which is really close to x. I think I'm going to use u substitution. If I take u to be x squared plus 4, the derivative of u is going to be 2x dx. I just want x dx, so it's going to be 1/2 of the derivative of u is equal to x times the derivative of x. And now I could substitute. So we have the integral. The x dx is the 1/2 du. And this is going to be the x squared on the bottom is going to be 1 over u. So that's u. The x dx is the 1/2 du. I don't know. Maybe it would have been, if this looks nicer to you, you could have written like 1/2 du over u. If that's what you were thinking when you substituted, this is all the same thing. Either way, we have 1 over u du, and we have this factor of 1/2. You could factor the 1/2 out if you want. It doesn't matter. I can put the 1/2 down there. Either way, when we integrate that, the right-hand side is still natural log of absolute value of y. This is just going to be 1/2 times the natural log of u. Natural log of the absolute value of u, and u, I remember, is x squared plus 4. So just plugging that back in. And we have some constant, and there it is. And I'm going to call it constant 1 for now. You don't have to be too careful with the constants because it's just a constant, and the constant could be anything. Now, we have we've done the integration part. Now we just need to see if we can isolate y, get y by itself. So I'm going to exponentiate both sides to get rid of the natural log. So e and the natural log are inverse functions, so they're going to do each other. The y is going to come down. It's a property of logs. And on the right side, I have e to this plus this. And I'm going to write a way to simplify that. And I'll explain why it works because it's a little bit tough to see here. But this is really the same thing as e to the, let's go a little skinny here, 1/2 natural log of, I'm going to get rid of the absolute value and just write it as x squared plus 4. Times e to the c1. Now I did a couple things there, and let's unpack it. I got rid of the absolute value. The reason why I got rid of the absolute value is because x squared plus 4 is never going to be negative. So taking the absolute value of it, it's not adding anything to it. The x squared, the smallest x squared can be, no matter what number you pick for x, is 0. And if I add 4 to 0, the smallest this thing can be is 4. And the absolute value of anything 4 or bigger isn't going to do anything. So I don't need the absolute value there. And then the reason why I have 2 e's here rather than 1 is, I guess I'm essentially using this idea that x to the 4th, say, times x to the 3rd, you add the exponents, so that's x to the 4 plus 3, or x to the 7. Now I'm going backwards, so I'm rewriting kind of something where I have x to, I don't know, x to the a plus b. I can break that up into x to the a times x to the b, and that's what I'm doing here. I have e to the, this plus this, so that's like my a plus b, and I can break that up into e to the a, or e to this, times e to that other piece, the c1. And that's fine. It's just a property of exponents that you did way back in algebra, but it's just kind of ramped up a lot with all the different letters and variables to intimidate you. Anyways, moving forward. Okay, so a couple things. We have the absolute value of y equals, now, this 1/2 here, when you have a number being multiplied by a constant, you can move that, it's another property, to the exponent of the argument. So the natural log of some number, if I'm multiplying the natural log by a constant, that's the same thing as taking the natural log of that number to the 8th power. So you can do that. That's a property of logs, and I'm going to do that here. So this is going to be e to the natural log of x squared plus 4 to the 1/2. And e to the c1, so e is a constant, and I'm raising it to a constant. So this is just some constant. So e to the c1 is just a constant. And we'll call it, I don't know, just capital C. So I'm going to call it C2 because I think we're going to have to do this again. So we have some constant, which is, e to C1, but again, it's just some constant. Now, properties of logs, the e and the natural log undo each other, which is going to make this look even nicer. And I'm going to get just the x squared plus 4 to the 1/2, but taking it to the 1/2 is the same thing as the square root. And I'm just going to move that C2 right here. And the absolute value I'm going to drop. And if I drop that, then I'll explain why that's okay in a second. I'm going to call C equal to plus or minus C2. So again, this constant is either plus or minus C2. So whether y was negative or positive, we're going to be okay because it's just some constant that I can make it positive or negative by making the constant positive or negative. So this is a general solution to the differential equation. Let's go ahead and check it. One more comment before I check it. On the problems that we're going to look at that involve like virus spread, population growth, the y values are normally positive. So we're, a lot of times we'll kind of take that for granted, but we'll just, like, knowing that y is positive, we'll drop the absolute value sometimes in those situations. Okay, so we're going to check it. So I need to plug what we got in for y over here, and I need to find its derivative and plug it in here and see if they're the same. So let's do it. So y is c times the square root of x squared plus 4. If I want to take the derivative of that, remember this is just c times x squared plus 4 to the 1/2. So if I want to take the derivative, it's just a chain rule. It's going to be 1/2 c times x squared plus 4 to the negative 1/2 times the derivative of the inside. The derivative of x squared plus 4 is just 2x. Again, let's see, those 2's are going to cancel out. And this is going to be, we have a c and the x up top, and on the bottom we have x squared plus 4 to the positive 1/2, which is the same thing as the square root. So let's check. We have x squared plus 4 times y prime, which we just said is this right here. This is y prime. So times cx times x squared plus 4. And is that equal to, so we can't like do anything to both sides. We should look at each side as kind of separate piece. X times y, and y was right up here. That's c times the square root of x squared plus 4. Are these the same? Well, I can simplify this right here. Both of these are x squared plus 4, and x squared plus 4 over the square root of x squared plus 4. Let me just rewrite that as x squared plus 4 to the 1/2. So when I'm dividing two numbers with the same base, I can just subtract the exponents. So 1 minus 1/2 is 1/2. So I have x squared plus 4 to the 1/2 times cx, which is the same thing as the square root of x squared plus 4 times cx, which is the same thing as we have over here. X times c times the square root of x squared plus 4. I mean, I could switch the xc to cx. It's the same thing. And it turns out that, yeah, we did it right. We got the same thing. A solution to this, the general solution to this is given right here. That's our general solution. So actually, I like this color. That's pretty cool. All right. Now, last example. This one's a little tricky because you're not going to be able to solve for y at the end. But let's just do our steps. We're going to find the particular solution. We know that it goes to the point 0, 1. And our goal is to find some equation that solves this. So let's see. Let's separate our variables. I'm going to first rewrite so dy and dx is already done. We have dy dx and it's already separated. I guess I'm just going to bring this term right here to the other side by subtracting it on both sides. So I'll get my dx on the other side. I'm going to do it in red. And right here we have e to the negative x squared times y squared minus 1 dy equals negative xy dx. And let's see, I want to continue to get my variables separated. So the first thing I'm going to do is going to get this e to the negative x squared on the other side so that I have it on the x side. And the way I'm going to do that is multiply both sides by e to the positive x squared. It's the same thing as dividing both sides by e to the negative x squared, but this is going to look nicer. So when I multiply e to the x squared times e to the negative x squared, you would add the exponents, and x squared plus negative x squared would be 0, which would make those cancel out. E to the 0 is 1, which is what we wanted. So I'll have y squared minus 1 times the derivative of y equals negative xy e to the x squared dx. And then to get rid of this y, I'm just going to divide it on both sides, and then we got our variables separated. Ooh. So just a lot of algebra, par for the course in calculus, right? And then we just got to integrate both sides. So we separated our variables. I got my y's on the left, my x's on the right. This left side I can simplify. This is the same thing as I'm just going to distribute the y in the denominator. So this is really y squared over y minus 1 over y. And that's the same thing as so y squared over y, that's going to be a y minus 1 over y. So kind of doing two steps in one there, but y squared divided by y is just y, and then 1 over y is just 1 over y. And the antiderivative of that, well, let's, gotta plug this in. So you could try doing this on your own too if you pause the video, but the right-hand side, we're going to integrate that. We're going to need u sub. For this side, it'll be a piece of cake. Let me just finish the left side first. So the antiderivative of y is going to be 1/2 y to the second. The antiderivative of 1 over y is natural log of the absolute value of y. And then on the right side, I'm going to need to use u substitution because I have e to the x squared, and that's the derivative of x squared is 2x, which is negative 2 times negative x, so we'll be able to just multiply by a constant and be okay. Ooh. So let's take u to be x squared. The derivative of u would be 2x dx. If I multiply both sides by negative 1/2. Then I'll get negative 1/2 du equals negative x dx, which is what I wanted right here. And so this is going to be the integral of, let's see, the negative x dx is my negative 1/2 du. So the negative x dx is negative 1/2 du. And the e to the x squared, we said x squared is u, right? So it's going to be e to the u. So now everything here is in terms of u. That's okay. When we take the antiderivative, it'll be a piece of cake. The antiderivative of negative 1/2 e to the u is negative 1/2 e to the u. And I'm going to replace u with x squared. And there's our constant. So the next step after doing the antiderivative would be to get y by itself, but you can't do it. There's no way you're going to get, to undo the squaring, we're going to need a square root. But then we also have a natural log of y. To undo the natural log, we'll have an exponential function. But then I'll have an exponential function on this y, and then to get rid of that, I'll need the natural log function. To get rid of that, then this function will be back to the natural log. There's no way to get these y's all together in one place. It's just not going to happen. And you can give it a try and maybe prove me wrong. What I do know is that it goes through the point, was it 0, 1? So if it goes through 0, 1, I can at least find the c value. So we know it goes through, come on, computer. Man, what a shame would that be if I had to restart this video. So we know it goes through 0, 1. So let's do it. So we have 1/2 y squared minus the natural log of the absolute value of y equals negative 1/2 e to the something squared plus some constant, and x is 0 and y is 1. And let's solve for c. It looks pretty intimidating, but zeros and ones are easy numbers to work with. 1 squared is 1. 1 times a half is a half. The natural log of 1 is 0. I don't know. That's something that it's kind of like knowing, like you know the sign of 0 is 0. You got to know the natural log of 1 is 1. When you're evaluating this, if you were to do it in your head, the question is e to what power is 1, and e to the 0 is 1. Use a calculator if you'd rather do that. E to the 0 is 1, so 1 times negative 1/2 is negative 1/2 plus c. So add a half to both sides. A half plus a half is 1, so c equals 1. And we pretty much finished here. So I have 1/2 y squared minus the natural log of y equals negative 1/2 e to the x squared plus c, which we know is 1. To clean this up, make it look a little bit nicer, maybe multiply both sides by 2. And that'll just get rid of the fraction. So I get y squared minus 2 natural log of the absolute value of y. Multiply that by 2, I just get negative e to the x squared. And multiply that by 2, I just get 2. And the book just added the e to the x squared to both, e to the x squared to both sides. So if I add that to both sides, I get positive e to the x squared on the left side. On the right side, it goes away. And I just get 2. So this is a nice solution here. And then that's it. That's the answer. That's what we get when we try to solve this differential equation. I don't have y by itself, but this is our particular solution to the differential equation, even though we don't have an explicit formula. We have an implicit formula. If you remember implicit differentiation, that happens sometimes. Anyways, I think that's it for this video. So just get some practice doing that this week.